But certainly this does not yet include what can happen if you go to future protocols, maybe, in which also solitons could play a role.
Have time for another question? Adapters that had been used in the first session that were adapters from mini display port, the one typical video output of Max that has disappeared from the previous session, and two of them, which is, so please, if anybody has tried or were the speaker in the previous session and just got wrong in a wrong way, the adapter attached to the computer, we would appreciate if it is brought back. Then the second announcement is that at the end of the session, please correct your posters, and if you need a certificate, please ask to the secretary to get your certificate. And finally, if you would like, or you don't need your badge and you'd like it to be recycled, there is a box at the exit that the badges can be recycled. So now we move on to the last talk of this session, which is going to be given by Professor Rajarshi Roy, and the talk is entitled "Seeing the Light," which is a statement, and then it follows at the end of the tunnel.
Okay, so let's see. Thank you. Well, I should say what a delight it's been for me to be here and to attend these wonderful talks that all of you have given, seen many of the posters from which I have learned so much, and to celebrate IFISC for 10 years, and particularly Maxi, who I have known for more years than he or I would admit. And it's just been such a marvelous journey to watch him and see how he leads and nurtures people over here. So it has been a great pleasure for me to come and to present to you something, but in a lighter vein. These two beautiful talks before me illustrated how much optics and light can do. And I wanted to attempt to tell you about very simple things. How do we see light, and how sometimes we shouldn't believe all that we see. Okay, so with that, let me try and see if I can get these slides to come on and work. Maybe not, maybe yes. Okay, this is fine, don't worry about it. Perfect. So, here is what I want to talk about. Life begins, a baby is born, and our eyes open, we start to see, and then we learn later on that some of the things that we see can be illusions. And so part of my talk will be about optical illusions, but about very simple apparatus that can be used to probe the connections between our eyes and the brain. Okay? How do we actually see things and interpret them? This is a very interesting and complex system that we have in our bodies. And so the complex system that I'll be thinking about is our bodies, light and dark, feedback loops, how we understand and interpret things that we actually see. So let's see. Yeah. Let's see. No? This one. This one, okay. Thank you so much. And you can see that my eyes and my brain take time to function properly. Okay, so here we are. And I want to start with something that is a very ancient prayer in Sanskrit. And it goes, Om Bhur Bhuva Swah Tatsaviturvarenyam bhargo devasya dhimahi dhiyo yonah prachodayat. And what it means is, a rough paraphrase is on the right, okay? And we meditate on the glory of that radiant being who has produced this universe, the earth and skies, may our minds be enlightened, okay? And this is a very ancient poem, and it uses 24 syllables, organized in a particular pattern, a pattern that human beings have responded to for thousands of years, okay? So sounds and words and meaning resonate inside us and create a concentration and an enlightenment that is very profound, okay? This has been the experience of people through a long, long time. Now let's look at ophthalmology and our eyes a little bit. And here's a little tidbit. Around 800 BC, Sushruta was a person who wrote one of the first ophthalmological texts. And he classified 76 ocular diseases, diseases of the eye, that he thought were very important, and he tried to perform cataract surgery. And the reason I show this is because I will come back to cataract surgery and how we can try to do this with lasers later on, okay? Now here's the other guy, you know, Ibn al-Hasan, Ibn al-Haytham, and you can see over here that he also wrote a book on optics. And he preceded, I think, by about 200 years, the origin of the scientific method. He wanted to have proof, experimental proof, added to speculation about how nature works. Okay? So this is a very interesting sort of way background history. But this is the person who is one of my heroes, Helmholtz, and he had students whom he encouraged to look for things, including Heinrich Hertz, who at the young age, in his late 20s and early 30s, was able to discover electromagnetic waves for the first time and created transmitters and receivers. And then, of course, some of the other students of Helmholtz you can see listed over here. So rather an interesting group of people that he nurtured and led. Now, so now this is working. Okay. So very interesting, right? So here's how the human eye looks. You can see that it has just a few basic elements in there, right? So here's the lens, here's the cornea above it, and inside the eye we have this thing called vitreous humor, and then the optic nerve takes the signals that come in and are generated by the rods and cones, which are the receptors. For color vision, we have three kinds of cones. For rods, we have monochromatic vision in low light, okay? And we'll address all of these things a little bit more later on, but you can see that the light comes in this way, creates responses in these receptors, and then the light gets all the signals sort of together and flowing out through the optic nerve to our brain, okay? So Helmholtz was really curious about how the eye works. And he was a very dedicated teacher, so one of the things that he did was to develop the first, okay? And the design that he came up for his instrument is pretty much the principle of even the most modern ophthalmic, viewing instruments, to look into a subject's eye and see the retina working, okay? So he created this very simple system, as you can see, of a light source, a mirror, shining light into the subject's eye, using a correcting lens, and then the examiner could actually see what the retina was doing, okay? So remarkable invention which has persisted for a long, long time. And then when you look at the retina, That's partly what it looks like. And here you see that when we image things on the retina, they're upside down. And when the brain interprets what we are looking at, we see things the right way up. Okay? And these are really very good things if the eye functions well. But what you can see sometimes with this ophthalmic instrument is that the eye doesn't function very well. Okay? Now here are the basic steps that are involved in seeing the light. So what you see over here is that when light hits a rod cell, it isomerizes a chemical called retinal, and then all these processes have to take place in order for the electrical impulse to be sent to the brain. Okay? So what happens with visible light is a geometric or cis-trans isomerism. Okay? The molecule changes shape physically, and that's what causes us to be able to see. So what you see over here are all the different steps. I won't go into the details over here. They're well documented, but it took a long time to actually work through and discover all these steps. And part of the issue is that as these steps happen, there's a time delay. So I'm very interested in time delay systems, and in the visual system there's a time delay that occurs. It takes time for light to get from the eye to the brain, and you can actually try and measure this latency or this time taken by the light to go from the eye to the brain with a meter stick. Sometimes I actually do this demonstration in front of people, but I think in view of the short time that I have, I will leave that demonstration out. Instead, what I will do is give you a demonstration of something else that I'm very fond of. It's how to balance things, okay? So if I try to balance this stick on my finger, okay, I'm fairly quick with my responses, but you can see that I can't balance it for very long, okay? So it fails miserably. But if I lengthen this stick, I have no problem at all, okay? Somewhere in between is a length. Still works, right? Okay? Let's see if it works here, right? I can still do it over here, but my actions are getting faster and faster. My feedback loops are having to accelerate, right? And then when I do it over here, I can't do it for more than a few seconds, okay? So that's a very interesting thing to understand. There's a feedback loop operating. My sensors are constantly feeding me with information that I have to process, and then I have to implement a control system to try and balance this. What is the critical length at which my control system fails? Very interesting question, right? Now, when we are children, when we are babies growing up, like I started my talk with, we have to learn how to balance things and not sticks. We have to learn how to balance ourselves. So what do toddlers do when they start to grow up? They start to walk, okay? And they discover that they can do that after a while. Many trial and error processes going on simultaneously, learning of information going on, and finally we can walk, okay? Riding a bicycle is very similar. We have to keep on trying to do this, and then we learn how to do it. It's a very, very hard problem to understand mathematically, okay? Now, if I can balance a stick on my finger, can I actually balance an eel on the end of my nose? Maybe some of you have seen this picture. Do any of you recognize where that illustration comes from? Alice in Wonderland, right? And who is that gentleman who's doing this wonderful balancing act? It's a person who's just celebrating his 65th birthday. Okay? So we will actually come to see more about this in a little while, but that's the person who's actually doing this amazing feat of acrobatics. "You are old," said the youth. "One would hardly suppose that your eye was as steady as ever. Yet you balanced an eel on the end of your nose. What made you, Father Maxi, so dreadfully clever?" Okay, so this is what we have to learn from here, is that balancing is a very, very critical thing. And the National Institutes of Health in the US spend a huge amount of money every year on people who fall and break their bones, okay, in different ways, injure themselves very badly sometimes, okay? So this is very serious business, actually. Now, let's take a look at some other problems with seeing. So one of the things that I wanted to just mention to you over here is retinitis pigmentosa. It's a way of the photoreceptors, the rods and cones, starting to lose their ability to create an image. And gradually, your eye starts to see less and less. And in fact, you develop this tunnel vision. Okay? So this starts to happen, and people actually go blind. Sometimes, it happens without too much warning. Now, the other kind of disease that is very familiar around the world is glaucoma. It's an eye disease in which the fluid pressure builds up inside the eyeball and creates a problem with seeing. And you see over here on the right a typical vision test that's done, a field test where lights are shined at different points on my visual field, and I have to press a button as soon as I see the light, okay? And when I see the light and press the button, it tries to see, this is a normal result, this is an eye where part of the field of vision has gotten damaged, okay? I myself discovered that I had this problem several years ago in one of my eyes, because I suddenly discovered that when I moved my finger around here, I couldn't see anything. Okay? So one of the things I would advise you all to do is from time to time test your vision, move your finger around, close one eye, and see if you can see it everywhere. Okay? This is a way to keep early detection of glaucoma and not suffer the consequences, which are laser surgery or taking drops every day several times, which is what I actually have gone through. So the first time I actually ever stared into a laser as an optical physicist, I was trained never to look into a laser, but I had to actually do that when the surgeon wanted to try and poke holes in my eye to get the fluid pressure to decrease, okay? And so these are really very interesting things that you learn as you go through life and you learn about seeing. Okay? A 532 nanometer laser, a doubled YAG laser, exactly the same frequency as this beam, was in fact aimed into my eye and drilled little holes in it. Okay? So these are the kinds of things that happen. Now, the much more common problem that many of you clearly, obviously have is the human eye often has myopia or presbyopia. Okay? And this is often called short sight or long sight. And you can see over here that the normal eye can focus from 25 centimeters, which is around here, to infinity. Okay? A nearsighted eye, such as my nearsighted eye over here, I cannot see anything clearly beyond this distance. A wonderful, simple equation, the lens equation, can actually tell you that this distance beyond which I can't see anything clearly is in fact the focal length of the correcting lens that I need here to correct my vision so that I will be able to see distances, out to infinity. So it's a very, very simple thing. But these are the problems of vision. And of course, you notice over here that all of these things rely on the eye being able to change the focal length of the lens using the ciliary muscles, okay, and then being able to focus on far objects or close by objects. And this is a remarkable property of the human eye that is emphasized in this figure, where you see that when we are young, okay, we have the ability to change or accommodate the focal length of our eye by many diopters. Okay? The focal length of a lens is measured in diopters, which is 1 over the focal length in meters. Okay? And we have enormous flexibility when we are young, but as we reach Maxi's age, something happens. We need glasses that have progressive lenses usually. So if you look at my glasses, the upper half is correction for myopia. The lower half is correction for accommodation. Okay? And these progressive lenses are wonderful. They're great advances in optics. And I think that eyeglasses or contact lenses are fantastic things, but I want to tell you a little more about different things here. And you notice I have the first eyeglasses were sold in Venice probably around 1286. Okay? This is a wonderful sort of thing to relate to Galileo's use of lenses to build the telescope. There were lens grinders in Italy who were really excellent craftspeople. Okay? So that's how that all worked. But now let's think about electromagnetic waves, which is what light is. And I want to mention to you that Hertz obtained his PhD from the University of Berlin and for the next 3 years remained to do postdoc work with Helmholtz. Okay? 1883 he went to Kiel and then he became a full professor at Karlsruhe. And you can see over here that when he was asked what applications did his electromagnetic waves have, he said it's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they're there. And that's what he was excited about. Okay? And asked about the ramifications of his discoveries, Hertz replied, nothing, I guess. There's a great virtue in being useless. Okay? This is something that I want to emphasize to all the young folks over here. Never try to be too useful. Take things very lightly and be as useless as you can and think as deeply as you can about all the things that you're doing. So this is something I really learned from Hertz. Now, take a look at the electromagnetic spectrum. It's amazing. It spans such a range of frequencies and wavelengths. It's pretty remarkable over here. And this is the visible length of the electromagnetic waves, 400 to 700 nanometers. And as you can see, this picture over here shows how light gets to us through the atmosphere. And this shows to you the 3 receptors that our cones have at the 3 different wavelengths. Okay? And that's where we get color vision from. So one of the very interesting things I wanted to introduce to you all, and perhaps some of you are familiar with him, but most may not be, is a gentleman named J.C. Bose, who came from the country that I came from, India. And in fact, he lived and taught in a city that was very close to where I was born. And J.C. Bose, in 1895, in a public demonstration in Kolkata, ignites gunpowder and rings a bell at a distance using millimeter range wavelength microwaves. And he wrote an article called Adrishyo Alok, which means invisible light. And he was a very interesting guy, and I want to tell you a little bit about his history. So this is J.C. Bose. He received a BA in Natural Sciences from the University of Cambridge and a BSc from the University of London and returned to India in 1885. He wanted to teach at a college over there, and he was told that he could teach, but that he would be paid 1/3 of what the other European professors at that college were paid. So he said, I protest, I'm not going to take any salary. And he taught for 3 years, over 20 hours per week, and spent his own money in building his laboratory and starting his experiments on electromagnetic waves, after which his principal and other people gave up, and they said, okay, we'll give all your money retroactively back that you are owed, and we'll pay you the same as the other people. Okay, so at that point, he said, okay, fine, I'm happy. He started taking the salary at that point. Okay, so it was a very interesting history, and his teachers were Lord Rayleigh and Sir Francis Darwin. Okay, so at Cambridge, and they both imparted to him an interest in electromagnetic waves and in the effect of light on plants. Plants see the light also, just as human beings and other animals do. Okay, and so he spent a good part of his life looking at the electrophysiology of plants and trying to understand the effect of light on plants. Now, this guy built all sorts of microwave apparatus in his very small and primitive lab in Kolkata. So it says over here, as you can see, that he carried on, he used waveguides, horn antennas, dielectric lenses, various polarizers, and even semiconductor detectors at frequencies as high as 60 gigahertz. And he was doing this in the 1890s, okay? And it says that, this is both at the Royal Institution doing a demonstration in 1897. So he was a really interesting character. And he filed a patent, 1904, didn't get anything for it, of course, but this was the first patent filed by an Indian in the United States, and that's why I wanted to show this to you. It's a detector for electrical disturbances, and it's something that you can look up, and you can see this is what his detector looked like. What's the shape of this object? This is his universal detector. It looks like the human eye, right? So that's what he modeled it after, and he called this an artificial retina. Okay, that was his name for it. And what he used over here was a crystal, a semiconductor crystal, to detect the light. And one of the very interesting things is that the word semiconductor, of course, was not known at that time. This was a lead sulfide crystal with a point contact, a tungsten wire, very sharp tungsten wire, that was a point contact, and he called it a universal radiometer and was awarded a patent for this. And a very similar device with a silicon crystal was invented here by Pickard in Massachusetts, okay? In 1906, he got that, and it created a huge effect. Bose's patent was completely forgotten, but Pickard's patent created a huge influence on the military, particularly. Got interested in detecting radio signals and using them for commercial and military applications. The other person who really found the right applications for radio waves was Marconi, who with Carl Ferdinand Braun got the Nobel Prize in 1909. And this was amazing also because he was only 20 or 21 years old when he began experiments at his father's country estate. And his father was so impressed with his experiments, he took his wallet out of his pocket and gave all the money he had to Marconi and said, son, go and patent this, go and develop these applications, and that's what Marconi went on to do. And it was really remarkable that this invention began to save lives from ships that were capsizing in the Atlantic Ocean, particularly the Titanic that you may have heard about or seen. Okay, so what about the artificial retina idea? Has this actually progressed, and what are people doing about it today? So here is a New York Times article from just a few years back when the patent was awarded and the Food and Drug Administration in the US first approved a system for an artificial retina that can be used by people with diseases like retinitis pigmentosa to actually see, okay? And this is a lady who was fitted with one of the early artificial retinas and developed by a biomedical engineer and an ophthalmologist, okay, Mark Humayun. And very interesting history to this, and there are really lovely videos of him explaining this artificial retina and his invention, how he worked at it and developed it over the years. Now, the other thing that optics can help with is doing things to the eye to shape our corneas. So I told you about glasses, such as what I wear, but this is an invention that came about much more recently, and as you can see, the excimer laser is a particular kind of laser where you have the ability to generate wavelengths which are really in the ultraviolet, okay? And these were built, first demonstrations were in the early 70s. That system over there is from 1973 or 74, around then, one of the first excimer lasers. And then these were developed, and you can see this is an Indian inventor who got some money for developing practical excimer lasers. His name is Mani Bhaumik, and he became a very rich man as a result of all this, and he just gave a huge amount of money to UCLA to found a theoretical physics institute there. Okay? So very interesting how inventions can sometimes actually help develop things in practical ways. Okay, so this is a story that maybe some of you know about. I have a few more minutes, Pera. So, and this was something that I heard firsthand from Jim Wynn, who was at IBM, and I'll tell you a little bit about it. So Jim Wynn is a guy who worked in nonlinear optics and did all sorts of interesting things there at IBM, but he had the foresight to buy an excimer laser for his group, okay? So he did that. And what he did was he realized around Thanksgiving of 1981, right after Thanksgiving, an interesting thing happened. This person in the middle, Srinivasan, Rangaswamy Srinivasan, who was a photochemist, brought in some leftover turkey from his Thanksgiving dinner, okay? And these guys decided they were going to try to do something with it. And what it did led to the National Medal of Technology and Innovation in 2011, okay? So let me show you, this is Sam Bloom, who's a materials engineer and scientist. This is Rangaswamy Srinivasan, and this is Jim Wynn. And what they did was the piece of turkey that Sri brought in, they actually carved it with the excimer laser and showed that the excimer laser could etch that cartilage, that turkey, piece of turkey, more finely than the neodymium YAG laser that you see over here, which is very poor, and it burns things up, okay? And the carving done by the excimer laser was exquisitely beautiful and clean, okay? So they discovered this right around Thanksgiving of 1981, and they went on to develop this, and the chemistry and physics of this, because Sri was a photochemist, they got to learn how to do this very carefully through a lot of work, but the idea is photoablation, okay? So the excimer laser has wavelengths short enough that its energy is absorbed and it vaporizes, ablates the material fast enough that no heat is really deposited there in appreciable amounts, okay? And what he was able to do is show that these create with pulses that are short enough and the laser wavelength that are short enough in wavelength as well, you can actually do this very cleanly. And this led to the use of argon fluoride lasers, excimer lasers, for this purpose, which really was looked at rather carefully by Srinivasan and Bodil Baron over here. And they were able to show that by shaping the cornea of the eye, you could actually compensate for eye problems like myopia or presbyopia very accurately, okay? And so this was their wonderful discovery that then was taken up by ophthalmologists and developed into what we today know as LASIK, okay? So how pervasive and safe is laser refractive surgery? So you can see 35 million people have undergone LASIK or photoradial keratomic surgery since the first sighted person volunteered to be a guinea pig in 1987. Okay? So it's just 30 years. And we have had 35 million people do this at this point. Okay? It's a very interesting thing to learn about. Just at the same time as these guys were doing that, there was an ophthalmologist who was worrying about cataracts. And we talked about cataracts. This is this becoming opaque. The lens becomes opaque. We still really don't know all the reasons for this happening, but Patricia Bath was an ophthalmologist who discovered just at the same time that with xenon chloride lasers, she could actually take cataracts out of the eye. Okay? So it was a very, very exciting and interesting time, and she developed a whole setup to actually do this and became one of the pioneers of laser cataract surgery. Now that we have 20/20 vision, should we believe all that we see? And you can see over here, this is how we sort of process things with the brain, and the brain can play tricks on us. So whose picture is this? Many of you know probably who drew this. It's Escher. Okay? But the amazing thing is that Escher actually knew physicists and scientists very well, and mathematicians. Okay? So this is the connection with Escher. So Roger Penrose was at a conference in Amsterdam, and he went and saw Escher's drawings. And he was so inspired, he came right back, and with his father, Lionel Penrose, wrote a wonderful article that you can see from 1958, okay, about impossible objects. Objects that, if you just trace them, seem to be okay, but then you realize there's something grossly wrong with what they're showing you, right? So the person, the mathematician who really also inspired Escher was Don Coxeter, very eminent geometer, and very interesting, those circle limits, 1, 2, 3, 4, a whole series of drawings that, paintings that Escher did, which are really quite interesting to think about and look at. Okay? Now here are some illusions. Yes, 5 minutes. Perfect. Here are some illusions that you can look at. Okay? Count the black dots. Many of you may have seen this, but it's really quite startling how simple things can confuse us. These are very simple and well-known illusions. How many legs does this elephant have? And counting them becomes very interesting as you try to look at this and think through it. So bistable, this is on color vision, left-right brain, conflict. And these are all very interesting and simple things. But color vision is very complex. And you can see that here are different ways of seeing color. Okay? We have 3 receptors. And with 3 receptors, we can see roughly 10 million colors. Okay? But there are shrimp which have many more receptors. Some of them have as many as 11 receptors, and they obviously can see many more colors. What they do with it, I'm not quite sure. But here's a new illusion that I wanted to show you. And this, maybe some of you have seen, but this is a picture which looks rather peculiar. And there's something strange going on about this, right? But now if you look at it, it looks perfectly normal. Okay? So there's something very interesting that our brain does, and let me see if I can work this. Is the sound on? Maybe this thing has a very nice sound system, right? I'll start this again. Let's put it here. No. Put it here. this one. No, this one. No? So the sound apparently is not working?
Maybe in your laptop the sound is...
No, it's not turned off. The sound is here.
If you have the speakers, we can put a microphone on the speakers.
Yeah. So what I'm going to do is I'm just going to, I have a speaker that I brought just in case, okay? So I'm going to see if I can make this work. Yes.
Hi. Apart from the obvious, is there anything odd about the way I look?
I can put this.
No, we're not going to change anything apart from which way up I am. As I turn the right way up, maybe things aren't quite what they seem. Now what we actually did was took my mouth and turned it upside down. And the same with my eyes. I may look a bit odd like this, but quite normal when turned upside down. Strange, eh?
Okay? So there are some very interesting optical illusions that you can see. And just very fast, I want to show you a few things here about the eye's ability to see single photons. Okay? So the eye is actually very sensitive. But if we want to record photons, then we use things like this, which is a single photon counter that can be bought for a few $1,000s and can record the incidence of single photons. And why is this interesting? One of the things that I have really gotten an interest in lately is how to generate random numbers using photonic devices. Okay? So you can see that there are multiple ways of doing things to generate random numbers. And von Neumann said anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Very well-known comment by him. Okay? And pseudo-random numbers are generated by computers using MATLAB, Python, whatever you want. But one of the very simple ways of generating random numbers is to count photons. Okay? And you shoot a photon, you count 1 if it goes that way, a 0 if it goes this way. And there are many, many other techniques for generating random numbers that have come about using complex systems such as chaotic lasers. And this started around 2008 when one of my friends, Atsushi Uchida in Japan, started to do experiments with chaotic semiconductor lasers with time-delayed feedback, and showed that he could generate random numbers at about 2 gigabits per second, which was at that time 3 to 4 orders of magnitude faster than anyone could generate them. Okay? Very interesting sort of things that he showed. And single photons and quantum random number generators are well known. And in our lab, we have utilized the same kind of optoelectronic feedback loop that was developed by a student from IFISC, Jan Chembo, with Laurent Larger and Pericolette and others, okay, working together. We have reconstructed that same kind of thing, and I want to end my talk here with showing you Aaron counting photons, but then putting together chaotic attractors, okay? So you can start to see the three-dimensional reconstruction of a chaotic attractor, okay? Starting with very small numbers of photons and then going up to large numbers of photons, and the whole deterministic structure starts to emerge from what was very stochastic to begin with. Okay? So, with that I will end. This is a comparison of recent optical random number generation methods. And you can see now we can generate random numbers at about hundreds of gigabits per second. Okay? So a big use of these things is Monte Carlo simulations. Another big use is encryption. But I'll end my talk here. But since this is a special celebration, I thought I would end it by showing you what I brought for Maxi. From the United States, this is something I brought for Maxi, okay? And what this is a book of 1 million random digits. So whenever Maxi feels bored with whatever he's doing, Maxi, please accept this as a gift that you can start to use. As a statistical physicist, he can do that. And just to pay my respects to Maxi and to tell you how much I appreciate him, I wanted to do this, which is I wanted to show you balancing, right? So how does one balance? Hera, you have to come up here and catch me if I fall, right? Okay. So I'm going to take off my shoes first of all, right? Okay. Here. And Hera, you have to hold the microphone close to my mouth. Okay? And you are old, Father William, the young man said, and your hair has become very white, and yet you incessantly stand on your head. You think at your age it is right? In my youth, Father William replied to his son, I thought it might injure the brain, but now that I'm absolutely sure I have none, why, I do it again and again. Okay? So with that, Maxi, many salutes to you, and thank you so much. If there's time for any.
Any question?
No questions?
Questions?
I think the important question okay.
No. Well, so thank you very much for this wonderful and inspiring talk. Coming back to the equilibrium of the short stick that you showed at the beginning, if you practice enough, you would be able to make it. What happens with your delay loop in that case?
So I think what you can do is you can increase your speed to a certain extent, but you cannot make it short enough to actually do it if the stick is very short, because the time it takes for it to fall gets quicker and quicker, right? So I think there's a length at which I won't be able to do it. It's a learning process, and the learning actually does help me to decrease the size of this thing for balancing, but I've never been able to make it to the smallest height. I didn't practice enough, clearly. But it's a very interesting question. What is the critical height at which I can do it? And can I time my responses and see how fast I can learn? What is the learning process? So it's a three-dimensional, it's a very hard, so if you look on the web, you will find hundreds of papers on just this problem, okay? With people attaching sensors to the stick and then watching exactly how it goes and how it falls. John Milton in California is one of the big experts on this. So there are actually hundreds of papers on this specific control problem. It's not a simple one. Yeah.
Question about the retina. I heard some years ago that people think that there is some pre-processing already in the retina, not only in the brain. So it's not working only in the brain, but already in the retina does some computer work or some pre-processing of the signal.
I see.
Which obviously also with some, it's called back projections also, that the brain can influence what the retina does.
I see. I see. So I don't know too much about this, Gunter. So I would love to learn about it. But one of the things that we do oftentimes is when we try to, for example, copy something that somebody else is doing, right? We do a replay of it in our brain before we actually try to perform that action. So we try to imagine how things are done, and then this creates, through what are often called mirror neurons, okay, a learning process that enables me to perform a task as complex as picking up a glass of water to drink it. Okay. So it's a very interesting thing to learn, but I do not know this particular thing where the pre-processing happens. So I would love to learn about it. Yeah. Okay?
Any other question? Well, if not, we thank Raj for the talk again. And now we go to the awards, to the best two posters presented by registered students, and the